Alright, so in this video we're going to have a look at differentiating the three trigonometric functions, cos, sine and tan. And much like e to the x and ln x, you're going to find the first derivative of these in the log tables on page 25. There is, however, a catch as we progress, but let's take a look at what they go to first of all. So let's have a look here. We have y equals cos x. And the log tables tell us that that goes to minus sine of x. Nice and straightforward. But what would happen then if we had y is equal to cos of 2x? And if you've watched the other videos, you would know that whenever we have this sort of scenario, we actually have a composite function, a function inside a function. And what we're looking at here is first, if we have an input x, we're going to multiply it by 2, and then we're going to get cos of that answer. So when we're differentiating, we need to remember to not only differentiate cos to sine or minus sine x, we need to also address this 2x here. So let's take a look at what that looks like. We're going to have dy dx is equal to, well, cos here goes to, we know it goes to minus sine, and nothing changes about it. I've kept everything the same. I didn't change the 2x in any way inside here. That's all stayed the same. All right. What we do need to remember, however, is that it is a composite function, and while I've differentiated the cos to minus sine 2x, we need to remember there's two functions, and I need to differentiate that 2x. So 2x goes to 2 if we get the first derivative of it. And so our final answer there is going to be minus 2 sine 2x. That's the derivative of cos 2x. What about another example then of y equals cos of x squared plus 2x? Let's take a look at that one. So again, we know from the log tables on page 25 that cos goes to minus sine. So I can write that. So cos goes to minus sine. I do not change anything in the bracket there. Nothing is changed. But I do need to remember that while I have successfully differentiated cos to sine, minus sine even, when I do that, what I have done is differentiated only the cos part, not addressed as of yet the fact that it is a composite function, meaning there's two functions going on here. I need to differentiate that guy inside there, so he's not done yet. So I need to multiply my cos by 2x plus 2. Where is that coming from? It's the first derivative of what was in our bracket here. So our final answer then becomes minus 2x plus 2 sine of x squared plus 2x. And you can leave it like that. You can multiply that out if you want, or you can leave it like that. All right, looking at sine then, some examples that we would have with sine, the exact same rules apply. So sine gets differentiated to cos x. That's in the log tables. Other examples then, what about sine of 2x? Well, again, remember it's a composite function. There's two things going on. You're getting 2 multiplied by x. That output then gets put into sine. So it's going to become, sine becomes cos. And remember, don't change the 2x inside there. So keep that part the same. Nothing about the bracket, so that you could draw a bracket in like that. Nothing about that has changed. What does change is on the outside, I multiply by 2. So it becomes 2 cos 2x. Looking at perhaps a slightly more complicated example, what if we had sine of e to the 2x? Okay, let's look at that. If I had sine of e to the 2x, well, sine goes to cos. And if you do that correctly, we looked at in exam papers, you will get marks for doing any correct differentiation, and that there is your first part, any correct differentiation. So you've got sine e to the 2x goes to cos e to the 2x. Now what do we need to remember is that this is actually a composite function. There's two functions going on. we need to remember to multiply by the e to the 2x differentiated, and go back and watch the e to the x if you don't know how I get this answer. The answer is going to be 2 e to the 2x. So go back please and watch the videos on e to the x if you haven't figured this out yet. So that there is what we're going to have, and then you can write out your final answer, 2e to the 2x times cos of e to the 2x, and there you have that one. And the last one then, tan, we didn't give much attention to during the lessons, but it is because it is very systematic and very easy. If you can do cos and sine, and you can do ln, and you can do e to the x, tan follows the same rules. So we're going to have a look at that. So dy dx of tan x goes to, if you look at page 25 of the log tables, that becomes sec squared of x. Then if we go and we say something like y is equal to tan, let's go for tan ln of x, right? And if you don't know how to differentiate that, please go back and watch the video we have on that. Tan, straight away, we know from the last one, tan will go to sec squared of whatever our x is, and in this case it's ln of x, so that becomes sec squared of ln of x. Now remember, that's a composite function. You're getting ln of x and then you're putting it inside to the tan. So you're going to have multiply that by the differential of ln x, which is 1 all over x. So you get sec squared ln of x. Multiply that out all over x. I'll do one more. Y is equal to tan of, let's say, e to the x squared. If we have that scenario, well, again, we get that our sec squared is what tan becomes, so we're going to write that and change nothing about the bracket. You don't differentiate the e to the x inside the bracket here. You save it for after, where you multiply by 2x e to the x squared. And again, if you don't know how I got that or where that came from, go and check out the other videos. So that stays the same, multiplied by 2x, and your sec squared has come from your tan. All right, and if you want to know why we multiplied by the differential of what was in there, look at the videos on u substitution.